Good morning, everyone. So this is the lambda hat paper, and it's Stan Say's joint work with Susan Wee and Daniel. And I think a lot of you here have know about it, and in fact have used it and use variants of it. So this will be just reporting on the paper, but for those of you who are also familiar with the work, feel free to interject and comment. Okay. All right. So the main goal is we want a way to compare the notion that we chose a very neutral word called a degeneracy or complexity of statistical learning machines, right? And we posit that the learning coefficient lambda, the RLCT, and the other name for it, introduced in SLT is a good notion of complexity. You can say that it is the right notion of complexity if you want to be provocative. So we'll introduce a localized version of this quantity, localized near a critical point W star, to measure a local notion of degeneracy or complexity. And then we will devise a method to estimate that local learning coefficient called lambda hat, and then we'll test it in various settings. Yes?
Can you remind the difference between learning coefficient and RLCT?
Good question. So, so for short, I think there will be a slide about that. So for short, I will use the more general and neutral term learning coefficient as it relates to SLT, which I will define in a moment. And RLCT is the algebraic notion coming. It's a notion coming from algebraic geometry related to quantifying the birational invariant of some variety. And we'll look at where that could differ later. Won't go through the setup of SLT. We have gone through that a lot. So there's data, there's model, there's a negative log likelihood. I will just use the word loss in the context of machine learning. There's a potential energy L, which is the average version of the loss over potential realization of data set. That's the Bayesian posterior. Z is a partition function. And then the free energy is negative log of Z. I'll point to it on the whiteboard later. Not going through it again. Okay, so definition of lambda. So learning coefficient or RLCT. So let L naught be the minimum of the potential energy over the entire parameter space. And here we already implicitly assume that this minimum exists and is attainable. That's why we call it minimum in the parameter space. We don't assume realizability, meaning we don't assume that there exists a parameter W naught such that W naught, the model at W naught is exactly the true distribution Q. We don't assume that, but we do assume a technical condition known as relatively finite variance, as Professor Aoyagi shown yesterday. It is a technical condition needed so that we can talk about, so that we can control the fluctuation of the potential energy L from its empirical version, the loss Ln. Okay, that's going to be the extent of caveats and assumptions that I'm going to talk about. But feel free to talk to me and read the paper for more details, or quiz me at the relevant section. Okay, let's define a very important function called K, which is L minus L naught. It's just zeroing, so think of it as zeroing out the potential. So just like in physics, the potential energy is not an absolute quantity, and we just pick a zero level. So K is, instead of talking about a minimum, we are talking about zeros of K. Now the zeta function is a very unique object. It's defined as so zeta of Z is a complex function. Z is a complex variable. It's defined as this integral over the parameter space. So it's K raised to the Z. Okay, so if Z has real part greater than 0, so on the right half plane. I believe I have that's okay. On the right half plane, so positive exponent, this is going to be well-defined integrable, and as a function of z, it is a holomorphic function on the right half plane. So for negative real part on the left half plane, the zeros of k starts to be a problem, right? When we actually attain the minimum of L, of our potential, when we are actually starting to get close to good solutions that is as close as possible to the true distribution. That is starting to become a problem. And it turns out that you can, holomorphic on the right half plane, and therefore you can analytically continue it to the entire plane. And under some assumptions of the analyticity of K and so on, you can prove that this becomes analytically continued to a meromorphic function. So it is analytic everywhere except for a few isolated points on the left half plane. And it's amazing that it's not just that, the poles are on the left half plane, not just that, they are on the negative real axis. Apology for the graphic. So this is a complex plane. The poles all lies on the negative real axis. Okay.
Is that a pole, literally standing on the pole?
Standing on, what? Sorry, what? Standing on the pole?
Just making a gameplay.
What are the lot? Oh, the arrows.
Sorry about yeah. Okay, lambda, the learning coefficient, is defined to be the largest. So now that it is on the negative real axis, meaning it is on the real number, it is actually orderable. So let's look at the largest one, meaning the one closest to 0.
Another sine error.
Oh!
The usual one.
The usual one. Okay. The picture is correct, right? It's all like that. It's that, right? The learning coefficient, lambda, is negative. Did I say that right? Negative of the largest pole. Okay. So the learning coefficient lambda is a positive value. It's let's just go modulus of the largest pole. There is no positive. So it's the modulus of the value of the largest pole.
Can the poles accumulate?
No, because this is a meromorphic function. Otherwise, it would not be a meromorphic function. Yeah. So under some assumptions, you can analytically continue.
Some assumption on K.
Yes. Yeah. Yeah. Okay. So that kind of okay. So there's another amazing fact, which is that not only is lambda a real value, not only do the pole lies on the negative real axis, it is actually a rational number. And that comes from Hironaka resolution on singularity. So you can, if K is an analytic function, then you can apply Hironaka resolution and actually evaluate this zeta function, and you can see that those poles are rational numbers. So that description of how you get to the poles using resolution on singularity, that is firmly in algebraic geometry. So that notion, we can call it the RLCT. However, the description, when K is no longer analytic, for example, piecewise analytic in the ReLU case, you can still evaluate this, and then you can still analytic continue it, and then you can still run SLT to get this notion of learning coefficient, right? So analyticity and being able to apply resolution singularity is a sufficient but not necessary condition. We do not know about the necessary condition for learning theory to work in general yet. Okay, so important thing about lambda is that it appears in, a very important thing is that it appears in the free energy formula as we have seen throughout the week, right? It's a log n term. just as a remark, this is where the relatively finite variance condition could come in. That the fact that it is the next order term other than the fit is related to the fact that there's no other terms in between. But okay, so for our context, this is where lambda is important. So let me defend the answer that lambda, the learning coefficient, is the right notion of complexity. Feel free to poke hole. Okay, so the principle of parsimony or Occam's razor is conventionally translated into for models that fit the data. For models that fit some data equally well, if you have multiple models that fits equally well, choose the one with the least parameter count. Okay, this is a very modern translation of a very old principle. Okay, in the context of statistical learning. So there is an incarnation of that principle in the form of Bayesian information criterion. So it's a model selection criterion. So if you have multiple competing models to explain a data, you choose the one that minimizes BIC, the Bayesian information criterion. So you can see that it is a competition between the fit, Ln, where W star is the maximum likelihood estimator. You have a parameterized model, you find the point in the model that minimizes your loss. So that's W star. And that's your fit, right? So for models with equal fit, you compare the next order term where D is the dimension of the model. How many parameters do you need to specify your model? That's the BIC. So BIC comes from the more general principle of free energy minimization. So it's saying that select model with minimum free energy. How do we get from free energy minimization to BIC? Well, that's coming from a theorem called Laplace approximation, where the free energy is negative log of the marginal likelihood. So you select model based on marginal likelihood, as we discussed before, is equivalent to finding the model that best fit your data when you average over all, when you marginalize over all model parameter. Okay, so if you have, Laplace approximation is a theorem that says that if you have a function f that is C2, that is twice continuously differentiable, and it has a unique global minimum, and that its Hessian matrix at the global minimum is non-singular. Well, since I'm calling it a global minimum, the Hessian have to be concave up. Therefore, it's positive definite. All its eigenvalues are positive. Right. So imagine a ball in 2D. Imagine an ellipsoid in higher dimensions. And the eigenvalues of the Hessian is the curvature. Major and minor axes. That's for ellipsoid. Yeah. Right. So and then the integral e to the negative nf times some positive function phi. So phi, think of it as a prior. So e to the negative n f of w, that integrand. And then we are interested in as n goes to infinity. So as n goes to infinity, nothing else except for the minima matters. Everything else gets exponentially suppressed, right? So this integrand is e to the negative n f at the minima times some correction factor involving the curvature. This is the Gaussian curvature, determinant of Hessian meaning the product of the eigenvalues, product of the principal curvatures. Right. That wouldn't work for if you don't have the positive definite. I didn't say anything wrong. So that wouldn't work for if your Hessian has a zero eigenvalue. this approximation just doesn't apply, right? Okay, so if we apply Laplace approximation to our potential function, then we get okay. I'm cheating a little bit here. I'm implicitly replacing L with Ln with L. So the marginal likelihood is a integration over Ln, but L is the expectation of Ln, and for large n they are close enough, and the condition of being close enough and not changing the character of this is the relatively finite variance condition. So if you apply Laplace approximation to our free energy, you get the free energy for the regular case, and the first couple of leading term is the BIC. That's regular model. Okay, so there's no degeneracy in regular model. And then the next step up is to introduce kind of a notion, a very familiar notion of degeneracy, meaning that there are some parameters that just don't matter. Okay, so if you have a model that fits the data, but that model doesn't depend on some parameter, obviously the integral doesn't, like, there's some of that integral has some coordinate that doesn't appear in your f, and that doesn't matter. Okay, but there's actually a more precise notion of that. That is, like, straight up you don't see the parameter in the model. But more precisely, we have the notion of Mossbot function. So we say the function is Mossbot f. So think about that as the L that we are going to apply it to. F is Mossbot if its set of critical points is a disjoint union of submanifold. So now think of those submanifold as parametrizing your models, the same models. Yes?
Is there a simple example you in mind?
A simple example. For example, L of x, y is equal to x squared plus y squared plus minus 1. And it has, it achieves square. Let me do that. So a slice of it will look like that, where at radius 1. So this is, yeah, so at radius 1, it achieves its minimum. So when r is equal to 1, achieve its minimum at the unit circle. And the minimum is 0.
Mexican hat potential.
Correct. The Mexican hat potential.
More generally, if your potential is invariant on the reaction of some
Yeah.
group, you have continuous group, you have.
Correct. So if you have some symmetry that you can, a continuous symmetry that you can travel along and leave your potential unperturbed, then you get a situation like this. Right? So that whole circle there is all critical points. So you get a critical submanifold, and it is like, to be a Mossbot, you need to be a smooth submanifold, and everywhere on that circle is giving you the same model. So you have 1 degree of freedom, not just not seeing the parameter, but there is a degree of freedom where you can travel that doesn't change your model. So intuitively, you don't need to specify as much, and intuitively your parameter count is 1 less in that example. Yes?
Or do they have to be the same model, or they have the same loss?
They're the same loss, but in the setting that we are in, relatively finite variance, they are the same model.
Right, of course,
Yeah.
And yeah, the second, this non-degenerate in a normal direction?
Yep, so I'm getting to that. So not only do we need, for it to be Mossbot, you need, you are non-degenerate in the normal direction, meaning if you mod out the continuous symmetry, then you get back just a non-degenerate function. So after you mod out the free parameters, you get back, and you get back a non-degenerate Hessian. So you look at the Hessian, and look at the normal direction to the critical submanifold. And in those directions, the Hessian is non-degenerate. So the upshot of that is that you, in that integral that we are trying to do just now, you, there is some directions where you, so you only need to apply Laplace to those directions where it is not degenerate. Okay, the intuitive notion is that this smooth submanifold is are the free parameters. Okay, so a Laplace approximation can be fixed by just applying the same theorem, but to a subset of those coordinates. And the upshot of that is that every time you have a free parameter in the sense of, okay, so the larger this manifold is in terms of dimension, the more dimension this manifold has, the more free parameters you have, the less, every time you have a free parameter, you decrease your model parameter count by 1.
So the class approximation, you also assume that the principal submanifold is compact, I guess.
Yes. Yes, throughout the entire talk, this is one of the technical assumptions that I didn't mention. All the integral exist, right? Okay. So the upshot is that the D on 2 term become codimension, meaning D minus number of free parameter. Okay, so these are kind of, we colloquially call them minimally singular models. So we are already in the realm of singular models. If you look at a official information matrix, it's going to be not positive definite. There are 0 eigenvalues, but it's morally still regular. Just close your eyes on some of those, right? But already we have the phenomenon of internal model selection that we have talked about in TMS1 before, which is if you have in different parts of a parameter space where you have, so locally near that parameter space, your local potential looks like has dimension 0, meaning it's a point, the minima is a point. So you have different critical submanifold. Some of them is a point, some of them is a line, some of them is a circle, some of them is a ball, etc. So here it's a point and a line. So as n increase, so everything else that away from the minima get exponentially suppressed. So I'm pulling e to the negative nl there, which is the integrand. And but then there is also a difference in importance between things with different codimensions. So the line is more important than the point in minimally singular models. And a blob is more important than a line. A hypercube is more important than blob, for example.
What do you mean by more important?
More important in the sense of contributing more posterior mass, contributing more to asking which model is more parsimonious, which model is less complex. But there are more severe forms of degeneracy than just having free parameters. So here's a plot. I'm not telling you what function it is. That's the set of minima of some two-dimensional functions, right? So it is a one-dimensional manifold. It looks like it has one free parameter. So if we look back at here, so this is it's akin to that situation. You have one free parameter, and you should. So if you look at this direction, you should see a Gaussian from here. So that's a Gaussian, and the Gaussian just gets sharper and sharper. Okay, but if I plot e to the negative n of this function, I get that. Okay, away from so it is somewhat Gaussian away from here. So it does look like it behaves minimally singularly away from that. But there is kind of a special point here where it takes up inordinate amount of mass, right? Or the mass is kind of flow to that point. Okay, I didn't. So to review the mystery function, this function is x to the 5 minus y cubed square. And the point is that that function does not have positive definite hashing. And the contribution to the posterior is not just from thinking about the curvature or thinking about how large the ellipsoid is. Right? So there is more severe form of degeneracy happening here, and they are important because they are where the posterior concentrate. So, right, so we have, for general singular models, the right asymptotic formula is given in SRT, and that's the free energy formula that we are familiar with. And the correct coefficient that give you the complexity term, so other than the fit term, is the RLCT, or more generally, the learning coefficient. And to I didn't. That's a mistake. Yeah. So there is a. Okay. So this is a fully. So we don't have a log n term in the previous two cases. In fully singular models, there is another term which is n minus 1 log n, and as we have seen in Professor Aoyagi's talk yesterday, that can be quite significant.
M is the multiplicity.
M is the multiplicity, so it is the order of the pole at lambda of the zeta function just now. Okay. So an alternative perspective of what lambda is the volume scaling perspective. So it's easy to visualize in one dimension. So the first two plot is just an x square plot with different hashing, with different curvature, right? So that's the first two plot. And if you perturb a little bit from the minima, for such a function, you move very quickly away. Your loss increase quite quickly if you are x square. But if you are half x square, you move less quickly. So the idea is that the volume of good. So the volume where y the volume of the set x such that y as a function of x is less than some epsilon is the volume that you can think of as good enough solutions, right? So for a regular model where you have quadratic potential well, that volume, so as epsilon becomes smaller and smaller, so as you want better and better solution, you need to specify closest to the optimum more. But for singular model, so this is an x to the 4 well, that volume goes down much slower. So the rate or the quantity that quantify the rate at which that volume shrinks is the RLCT. Right. So the RLCT for this case is 1/4. So the volume goes down much slower, and for that is 1/2. Okay. So from the perspective of internal model selection, or just model selection in general. Counting, so this is the upshot of that is counting free parameter is not sufficient as a notion of complexity, or so Occam's razor should not be just translated to for things with similar fit, choose the least parameter count. It's a little bit more than that, right? Right. So this is an example of a potential energy function, and that's the posterior of it at different n. So this is an illustration where if you just naively count free parameter, so the line has one free parameter, conventional wisdom would say that that is less complex and therefore the posterior would like it more. But, and the point, so the blob there is concentrated near a point, has no free parameter, but asymptotically, as n goes to very large, the point, that part actually has much larger volume than the line. Much larger probability mass and much larger volume asymptotically as epsilon goes to 0. Okay, so looking at this picture tells us that we kind of also want a notion of localized version of that complexity measure, so that within one model and within different parts of the parameter space, we can get this notion of complexity or probability mass concentration. Okay, so we want to tell the complexity of a given train parameter locally near W star. For modern large model, it is another reason we care about local notion is that we are quite unlikely to, in modern large model, to be at a global minimum of either Ln or L, right? We also wish to track the change in complexity if you, or the complexity of multiple different places and compare them. That's the internal model selection. And if you are training your model using something like SGD, to tracking the change in complexity across training could tell you something about how your model, your neural network is developing. Okay, and also just as a practical issue, global sampling is hard. So to get to the global lambda, the global learning coefficient is the volume scaling and then posterior mass concentration at the minimum loss, and that requires sampling near the global minimum, and that is infeasible for a large model. Okay, so we define a localized version of lambda via the same kind of deduction that we went through last time in TMS and in Dan's lecture. As a lot of you probably know, that there is some theoretical issues with this, how to pick a partition and so on, right? But
why do we have to frame it this way? We don't do it in a paper like this. This just makes people think that the discussion today hinges on these technical issues, which is not true.
Right, so yeah, okay, so you don't need to partition and then look at the complexity of that partition. This work is more like you have a point, pick a neighborhood around that point and look at the concentration near that. Yes?
So, if I understood you right, the problem with doing this for larger models is that this is defined at global minima and we're usually not at global minima. Can't you make yourself up a different loss function for which you are at the global minimum?
That is the point.
In, you find some behavioral loss or something.
Correct.
And say, for this input-output mapping, how many things degenerately have the same input-output mapping? And that defines an RCT probably again, and you just measure that.
Yes, yes. So another way to look at this is to say that instead of looking at the global infimum and instead of looking at the global minimum free energy, you are at a critical point, you are at a, let's say, local minimum, and then you just define your zero potential up there, up to that level.
What you said is exactly what I learned.
Correct.
Yeah, you just cut off the loss outside the neighborhood. You just look inside the neighborhood.
But that still assumes that within the original shape of the loss function, this is at least a local minimum. Whereas what I'm proposing is not assuming that. Like, I'm literally saying, make up any loss function, not like subtract a constant, but like just say, from now on, I measure, I don't know, the mean squared divergence from the input-output mapping here. And I just ask what in this neighborhood degenerately has that same input-output mapping. But you can do anywhere, you don't need local anymore.
But the relation of that to the complexity of the original model is pretty unclear.
Yes. You are changing L, you are changing the potential. But it is sensible though. Yeah. Yeah.
Sounds like a very interesting discussion.
It is interesting, and it can probably work out and see what changes. Okay, so the rest of the talk will be looking at devising a way to estimate this local complexity measure, the lambda hat at W star, and the core apparatus is introduced by Watanabe in what we call the WBIC paper, where a new information criterion, not the BIC, but the WBIC, the widely applicable Bayesian information criterion, or Watanabe information criterion, is defined to be the expectation of your log likelihood, so NL is the log likelihood, is a posterior expectation taken at a tempered posterior. So a tempered posterior is the same posterior, just with you introduce a temperature term to trade off how much you focus on the likelihood, or in colloquial terms, how much you update from your prior. And for WBIC is defined to be the temperature at which WBIC is defined is the beta star is equal to 1 over log n, where n is your data set size. So that's the definition, and with that, it is proven that the WBIC matches the free energy to leading order. Okay, and using that formula, we can get a procedure for. This is a proposed procedure for estimating local lambda. So, given that you are at a critical point, local minima, or a variance of it, and the model loss function, Ln, so set beta to be 1 over log n, generate samples Wj's from localized tempered posterior. Okay, bottle that, we will look at that. So now you have generate a bunch of samples from the posterior. The posterior average is just evaluating and taking mean, right? So here, the MCMC, so this is the MCMC estimated WBIC is equal to the posterior average. And here, I didn't write it out, but here I'm writing this out as kind of this weird notation. No, this is not. This not no weird notation here. So the M is the number of samples, and then you're just taking sample average. And yeah.
What is the hat over the WBIC?
Yeah, so WBIC is defined to be the posterior average. I'm just putting a hat there in the statistics convention of this is estimated from some samples, from some posterior samples. Right, and lambda hat is you rearrange the WBIC formula, and the next order term is a decaying term. Yes.
Yeah, can you remind where this comes from? The WBIC is the expectation of
That's my custom model.
Oh yeah.
Why? Because WBIC is log likelihood plus lambda log n, right? So where is this expectation? And
The WBIC is by definition the left-hand side, which is independent. I mean, it's independently defined as the expectation.
Why this formula is that is my custom model.
Yeah. So this is the definition of WBIC, and then it is proven that with this definition you get this behavior, this asymptotic behavior, and so.
And the proof is roughly similar to the extension.
Ask that.
It's more complicated. It's my type.
Okay.
Yeah. So look forward to that. Okay. So in this procedure, this is a general sort of recipe. There are some sort of major consideration here. So one consideration is we want a local version of this complexity measure. So we want to sample from a localized tempered posterior distribution, right? So one way to do that is to, well, you can set a bounding box, but so there's many technical consideration, and this is possibly one thing that we as a group can work on. But just reporting a choice that we made, which is so you always sample your sampler always start at W star, so you're already there, and while you are running the sampling, you introduce kind of a gentle quadratic restoring force, so Hooke's law. And that is just equivalent to saying that we introduce sort of a Gaussian prior with some hyperparameter, gamma, which is that's a spring constant of the Hooke's law, or the 1/, variance of the Gaussian prior. So that's how to localize. And then there is the question of how to sample. So there's these two big consideration that we can innovate on. But here, there's some requirements for the sampler is that it should be scalable. We want it to scalable because we want to apply it to large models. But the sampler only need to be local. The samples only need to be local, right? We don't need it to burn in and find the global minima. In fact, we don't want it to find lower energy states, for example. We want it to be where we are. We want to explore just the local geometries. Okay, so that's a weird sentence, sorry. So in this work, we choose in this work, we ask the question, is the most naive, scalable sampler, so the very popular stochastic gradient Langevin dynamics, the SGLD, is that sufficient? Right, so what that is that you do SGD, except every step you add in a Gaussian noise, right? So the SGD is the gradient descent is gradient descending on the loss as well as that restoring force. Right. Yes.
So I guess maybe do you want to talk more about why you choose like SGLD versus MCMC versus?
Right.
Yeah.
Right. So. Compared to, so why not other kind of Markov chain Monte Carlo sampler? Let's just contrast that with Metropolis Hastings, the one where you take a random steps and then evaluate whether or not you are going uphill or downhill, and accept or reject based on that. If you are in a million dimension space, that exploration is going to be non-gradient guided exploration is going to be super slow. So the SGLD has the extra signal of the steps that you take, despite having randomness, despite having Gaussian randomness, is roughly in the direction of going down. Yeah.
Maybe finish
Yeah.
that first.
Oh, and compared to like HMC, I guess. Just trying
Right.
to get you like a mini batch points.
Thank you. Yes. So SGLD, the S part of that, so also has the advantage of, so just like SGD, you can evaluate the gradient on you evaluate the gradient on mini batch. So you don't need to evaluate gradient on the full data set, which can be very large and very expensive. Yes.
So looking at this restoring force you're producing here, I'm sort of mentally imagining that I'm at this point, and I have a little rubber band where whenever I go too far away from the point, I get drawn back.
Correct.
But intuitively, what it feels like what I want more is that in directions that are very flat, I want to explore more, and directions that are less flat, I want to explore less.
Correct.
So what I'm imagining is more my sampler starts out with some kind of speed, like it's a little ball rolling around.
Yep.
And when it goes uphill too much in a direction, then the speed is gone and it's going to roll back.
Correct. Except you need to have that for arbitrary geometry of posterior. So you need to apply this algorithm for many different kinds, right? But that's the role of the gradient part. I will talk more about that that part in a bit. Okay. Sorry, that's okay. So some results. This is kind of asking whether or not this is sufficient to get. Is SGLDR sufficient? Can we actually detect the correct local complexity? So we run this on toy potentials, and so normal crossing form has a special place in SLT. It is kind of a normal form where you can make a change of coordinate to. And it is also a setting in which we know the RLCT. So this is just running this algorithm, running SGLD on L of W being normal crossing, so being x square, y square. So this one will be x square, y square. This one will be x square, y to the 4. So different levels of degeneracy. And then each one of these will have, you can apply SLT or integrate the zeta function and get the RLCT. So on the x-axis, on the graph on the left is the true RLCT lambda, and on the y-axis is lambda hat. It's estimated lambda hat. There's some error bar. You run multiple different estimation, and because this is a small enough model, we also run it using MCMC for comparison. So the black dots there are SGLD trajectory, and those are the samples that we plug into the posterior averages. So the dotted line is the lambda equal lambda hat line, so where you want to be. And well, MCMC does well, the blue dots, and SGLD with kind of different hyperparameter seems to also do well in this toy 2D examples. So to respond to your question as well, so SGLD is already aware of where the degenerate things are, and it sort of explore the degenerate directions, and it's aware of other features of local geometry. Okay, so we were looking at that line versus point. So we want to also show that this estimation of local complexity is not doing the naive parameter counting thing, right? So if you run through the integral, you will see that the point, as we said just now, has lower complexity, lower RLCT at 1/4. That's the first dotted line. And the line, well, the line is the one where this is chosen to be Mossbot. So the line has, well, this is 2-dimensional, and the line has 1 free parameter, so it's 2 minus 1 codimension. So it's so d onto coding onto is 1/2. So that's 1/2. So if you run SGLD on that, so you can see that the estimated lambda hat do concentrate near the correct point, near the correct values. Okay, those are verification in settings. Thank you. In settings that we have the theoretical value and we can visualize and check everything. Now here's kind of jumping way above the difficulty scale to running the algorithms, because just to show that it is scalable to million parameters feed-forward network. So this is a feed-forward network with around 1.8 million parameters on the MNIST dataset with 2 different optimizer. So here's where here's the advantage of being able to track local complexity, which is as you train, maybe with different optimizer, maybe with different configuration, with different loss, with different penalty, etc. How does the complexity evolve over training time? Well, this is, so we are comparing 2 different kind of training algorithm. One is just vanilla SGD, detail of those setting in the paper. And the other one is entropy SGD. So it is an optimizer that's designed specifically to minimize free energy, minimize the free energy. So not just the loss. So the idea is you generate some sample from local posterior, generate some sample from the local, everywhere you are, generate some sample from the local posterior, and you use those samples to estimate your free energy, and then you differentiate that, and then gradient descent on that signal. Okay, so the idea is that it should go to lower complexity. It should give you lower complexity solution. Yes.
You do this estimation for all of the weights in the network, right? How exactly do you do this for AWS?
What do you mean all the weights?
So you said like 1.8 million parameters, right?
Mm.
So how exactly do you do the posterior estimation there?
Right. So SGL. So you have this model. You have the loss. The loss is function of all the weights, 1.8 million weights.
Yeah.
So you do SGLD. So you take some mini batch, evaluate the gradient on that mini batch, and then step, add Gaussian noise. Do that many times.
So you do this on the entire network, or do you like freeze layers?
No, entire network.
On the entire network.
Entire network. Yes. Yes, and so freezing and looking at sub networks is the kind of purview of things that we should be thinking about. Yes?
To be clear, ESGD is not something that's an existing thing, right?
ESGD is an existing, I forgot the authors, check the references. Yeah. Oh, sorry, yeah.
So you do these SGLD stats in order to get the posterior, in order to get the local posterior, and then you calculate the grade, as in you just calculate the WBNC at this point and then differentiate it. Is that basically what you're doing? Sorry, how are you calculating the free energy at this stage?
I think it's the black box in
ESGD is another optimizer. Yeah, it's something that is specifically designed to not just minimize loss, but minimize loss and trade it off with complexity.
Yeah.
Right. And so this is over training time epoch. Over training time epoch, and then the estimated RLCT. I will take your question afterwards. So that's the HDE line, and that's the ESGD line. And it does turn out to be lower. And the other surprising feature is that a priori we didn't expect the estimation to be this consistent, meaning if you run multiple times over different training trajectory, different mini batches, different SGLD initialization, it surprised us a little bit that it is the variance is that small. Yes.
Were you using weight regularization with SGD or not?
No, just vanilla SGD, not even momentum. Oh wait, there is momentum. Yeah, just SGD with momentum. Yes.
Do these lines track similarly to the loss curves?
No. Wait. So the loss curve is just. So there's no surprising features here. So loss curve is also the not surprising.
Like, do these plateau at the same time loss plateaus?
Not sure. The loss curve is in the paper. We can look at that. Yeah. Okay, so we have twice verification in low-dimensional normal crossing potentials, but there's like other verification that we have done that has happened since then. So in TMS1, we have looked at, so we use the same algorithm in the TMS1 that we have seen. So that's that picture that you have seen. So the green curve there is lambda hat across training. So TMS is kind of a setting in which it's non-trivial, it's outside, it's not toy. Well, it's a toy model, but not toy specifically for this application. But the important thing is that we still have access to the theoretical RLCT with some very heavy calculations needed. But we have that, and we did check that it can recover the correct value. Initially, we pitched this as a way to compare degeneracy. So we want to say that a degeneracy, if the lambda hat is smaller, then the degeneracy is smaller in the ordering sense. So we are pleasantly surprised that at least in models that we have checked, it seems to also be accurate as well as preserving order as well. So I also want to mention the work by Nina and Dimitri in the modular addition. It is kind of the next step up, where we don't actually have access to the RLCT, but there is like they did a lot of mechanistic interpretation, and there's some notion of complexity independent other more heuristic notion of complexity that you can compare it against, and I believe they will be giving a talk on that very soon. So so here's kind of one of their results that I will leave them to talk about. It's I would say to me it's very impressive and surprising. There are also other settings that we have looked at, which is so one application that we wish to do is to use this to detect sudden changes in geometry, so phase transitions. So we did that in TMS, and we do see that lambda hat can detect that change. This is deep linear network, and since Professor Aoyagi talked, we actually have a big model with theoretical access to RLCT, so we are excited to probably write tests and verify it there as well. There are many open problems, so we want to use maybe similar techniques to look at to estimate singular fluctuations. Lambda is birational invariant is lambda hat. Can we use a different estimator, things different from WBIC? That's a purview of probably what Zai will talk about. And there are many experimental things that we should be doing to pile on the evidence that this measure on complexity has does not break when you scale up, does not break when it's not sensitive to mini batch size or things like that, for example. Okay. Okay, I will end it there, but I'll end it with just saying that there's a lot of us who have run this algorithm and have sort of collected some intuition about what could break. So things like the localizing prior that has been shown to be break very easily. And there are some intuition of how to tune the hyperparameter and how to find hyperparameter in an efficient way. So talk to us. Cool, thank you.